Well, where's everyone? Again, don't be late, please. Okay, so and there we have Krutika, right? You are with us? Can you listen to me? I think you can talk, right? Yes. Okay, she said yes. All right, that's enough. Good. So, guys, um, so previous lecture we finished with this brief introduction to measure theory. All right. So that's all we needed to know. That's all we need to know. During the exam, I will ask you questions about that, but just the main idea. All right. The main idea. I can ask you how do we get an algebra, right? So how do we get an algebra? So you would have to tell me like, look, we can, first of all, we don't need just an algebra from zero, right? We can just get something simpler called a semi-ring. From there, we get a ring. And if this ring has a universal set, then we have an algebra, right? Good. And I will tell you, okay, good. And how do we get a sigma algebra, right? And then how do we get the sigma algebra? And you would have to tell me, all right, if you want to define a sigma algebra, of course, this is a more complex set than an algebra because this set is closed under countable union of sets. So we need to define the outer measure, right, the Lebesgue outer measure, and then somehow we can compare if we have this universal set E, right, then we can take any set from E, let's call it A, right? And then for any set from equal that we call A, we can define the outer measure. And if this measure, so if we have the following, that for that the outer measure of A epsilon with A is less than some epsilon, where epsilon is greater than 0, right? So for all such A, there exists some A epsilon, right? Then it means that the set of all these A is, we call it M. And this is the set of measurable sets, right? M. And yeah, and M is not only an algebra, but M is also a sigma algebra, right? So in this way, we can get the sigma algebra that we want. Right. So, and now we have the sigma algebra, and now we can say that actually this measure, this outer measure, which wasn't a measure, if we apply it only to M, then this measure, this is going to be first a measure, and second of all, not only a measure, but a sigma additive measure, right? So we have a sigma algebra, and we have a measure on it, and this measure is sigma additive, right? And we call this the Lebesgue measure. And then there are, depending on how we define the measure M, little m on S, right? Depending on how we define this, then we define the classical Lebesgue measure, right? So the classical Lebesgue measure for any interval A and B that we know is just B minus A and so on, right? And this is all that we know. And then in the case when we have the following, so in the case, so when we talk about the probability space, we always were talking about omega and F, right? So the sample space and the sigma algebra. But now, instead of talking about omega, let's talk about all the real numbers, right? And F, so for the sigma algebra, we're going to take the Borel sigma algebra, right? And I can ask you what the Borel sigma algebra is. So a Borel sigma algebra, in words, this is the minimal sigma algebra which contains all the open sets, right? Well, let me write this in words. So this is the minimal sigma algebra containing all open sets in R, right? the minimal, the Borel sigma algebra. So this is the Borel sigma algebra. All right. That's big. Yeah, good. So this is the Borel sigma algebra, but we can express somehow this. So this is, what do we have here? We have this union. So this is the following set, the union of all such xi, where xi belongs to, we can have, for example, this set, so all the real numbers from minus infinite to some x close here, or we can have from minus infinite to open x, or we can have some a and b open here, or we can have close, and so on, right? So the union of all these sets is called a Borel sigma algebra, right? So this is a Borel sigma algebra, and all of this is contained inside this sigma algebra. Great. So we have this, so we have R, and we have the Borel sigma algebra. And we call this a measurable space. Right? And then, since we have this, we can define a measure in this. And we define the following measure. So we have, again, we have R, we have the Borel sigma algebra, and we have a measure. And this measure is such that this measure goes from the Borel sigma algebra to the set of all the numbers from between 0 and 1. All right? So this is a measure. And we call this measure probability measure. So this is the probability measure. Right? So this is a measure, the same measure that we saw before. This is just a measure, right? But the difference is that it goes from here to 0 and 1, not to the set of all real numbers, just for, to 0 and 1, okay? And this is called a probability measure. Now, we can see that this function, so this is a function, right? So let me remind you that this p from here, so this is a function, right? What kind of function is this? So this is a function from every Borel set. A Borel set is a set from the Borel sigma algebra, okay? For example, this is a Borel set, this is a Borel set, all of these are Borel sets, okay? So for every possible Borel set, we can define a probability. So we can define a number from 0 to 1. And this is the probability, okay? So we can define that the probability of minus infinite to x, and this is some number from 0 to 1, right? So some number there, okay? And we can do that for all of it. But if we want to describe probability, if we want to describe this function, it's very difficult to do it for each of these possible sets. So we are going to do it just for these sets, from minus infinite to x. So we are going to define a new function, right? So from p, we get a new function based on p, f of x, that by definition is the probability, so the measure of minus infinite to x. All right? So this is the definition of this function f, and we call this function the Cdf, the cumulative distribution function. Good. And now it means that for every time, if we want to describe this probability space, we don't need P, right? We don't need this large and difficult function. All we need is F, the CDF, right? This is all we need. Okay? And this is all that you should know by now. I mean, from these 4 lectures or 5 or 3, I don't remember, that we had, this is all that you should know. Okay? Good. Now, let's get back to this just in 10 minutes. But before that, let me talk about what? The probability space, right? So everything that you already know. So we have omega, we have F, and we have P, right? You know this, you know omega is just the sample space, you know this is the sigma algebra, and let me remind you, so F, the sigma algebra, what does it mean? First of all, so we need 3 conditions, right, for a set to be sigma algebra. So the first condition is that omega is an element of F, right? The second condition is that if A is an element of F, then the complement of A is also an element of F, right? And finally, if we have a countable union, a countable number of sets, right? Then the countable union of these sets is, and each of them is an element of F, then the countable union of these sets is also an element of F, right? So this is the definition of a sigma algebra, okay? And we had 3 lectures trying to define what a sigma algebra is. I could just tell you this and that's it. And that's actually what everyone does in probability theory. But I just wanted to give you like an introduction where this is coming from, right? So we already know what the sigma algebra is. Good. So this is check, and now we have to talk still about P, right? So the probability measure. So the properties. So the properties of this P. So first, the probability of omega is 1. Right. Second, the probability of the complement of A is 1 minus the probability of A. Yeah. And now, and this is the property that we call sigma additive, right? So the probability of the union, yeah, the probability, now let me define it like this. Yes. So number 3, if we have that a countable number of sets of events, right? And we know that they don't intersect. So for AI, the intersection with AJ is empty. For all I and J different, they don't intersect, right? Then the probability of the union, the countable union of these sets, give us just the sum of each of them, right? The countable sum from 1 to infinity of P of A. So we have that this property is, we call this property sigma additive. Right? Good. Great. So if you know all of this, you, I think, already have at least 3 on your exam. I mean, this is well, actually, if you don't know this, you don't have at least 3. You fail. right? Yeah, that's a different statement, right? So this, because I've been talking about this like for, I don't know, 2 months. If you combine all the lectures talking about that. So we have that, right? But this is not all that we need. So there's something else, and I'm going to talk about that right now. Okay, let's say. Now, what about this probability P? We need something else. There's a property. Just see if I don't need to tell you something else before. Yeah. So this property is called the continuity property of P. Continuity, I think. The difference. Huh? Continuity. All right, you got it. Something's wrong here. I just don't continue. All right. So this property tells us the following. If you have, so if you have sets like let me do that over here. This is A1, A2, A3, and so on. So we call this an increasing sequence of sets, right? So we have an increasing sequence of sets, A1, which is containing A2, which is containing A3, and so on. We call this an increasing, let me write that over here, sequence of sets. I'm sure this is not the first time you look at this. So we have these sets which are getting bigger and bigger, right? Then the probability, then what? Then the limit for n tending to infinity of AI is equal to what? Yeah, increasing. Yeah, so bigger, 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 bigger. So the limit of this sequence, well, this is a sequence, of course, there's a limit, right? So you already know that if we have numbers, then you can define a limit. So the same with sets. If you have set, you have a sequence of sets, you can define a limit. If this sequence is increasing, then the limit of the sequence is just the union of all of them, right? The union. So this is the union from 1 to infinity of AI. Okay? This is the first time you, maybe in calculus, you already look at something like this. No? The limit of, all right. This is if we have an increasing sequence. But we also can have a decreasing sequence, right? In that case, we have A1, which is big. All right. We have A1, which is big, and all the other sets are contained inside. So A1, A2, A3, and so on. No, you can change it by B, right? So we have an increasing sequence is when this is getting bigger and bigger and bigger, right? And a decreasing is when this is getting smaller, smaller, smaller. And this goes to infinity, right? To infinity in both cases. Now, if we have, so this is the first case. And the second case, if we have that A1 contains A2 and A2 contains A3, and so on, right? So this is a decreasing sequence. Then the limit of for n tending to infinity of ai, sorry, of here we have n, right? N is tending to infinity, this number from here, n, right? So a1, a2. What do you think should I write here? If here we have the union, then we have here the intersection, right? Because the limit is going to be the intersection of all of it. But this is the intersection. I hope this is clear. Okay, let me do this. Yeah, it's working. Okay, I think it's working. So this is the intersection, the countable intersection of all these sets. And the countable intersection of all these sets is just the empty set, right? So yeah, the limit is the empty set. Okay, so good. Look, we have two cases. We have increasing sets, increasing sequence of sets. We have a decreasing sequence of sets. In that case, we can see that. So for this case, and let me write this in this color. So for the first case, we see that the probability of the, how to write it? Yeah, the probability of, let's check, the union is the limit. Yeah, like the probability of the union from 1 to infinity of ai is just the limit. Okay, let me write it in front. It's the probability of the limit when n tends to infinity of an. And here comes the important thing. We can take this limit out. All right. So here we have the limit when n tends to infinity of the probability of an. With what? With, well, the probability gives you what? 0, right? That's it. So in this case we have this, but in this case, of course, the probability of the intersection of all these sets is just the limit n tends to infinity of probability of an, and this is 0. Well, actually, the other way. Well, you got it. What's the meaning of this? If you have a limit inside the probability, you can take it out. Just like that. This is the meaning of this property. Continue the property. If you have a limit, you can take it out. Good. All right. Now, what do we need all of that? Let me show you. Well, now we can go back to the probability distribution. Okay, so we already know this, and we need this property. So this property is very important. Okay, and we need it because we need to prove the properties of the CDF. All right. So again, we have f of x. We call this the CDF. Okay. Notice that we haven't talked about the random variable. All right. We've been talking about just a function p. We haven't talked about random variable. So a probability distribution, if you define a probability distribution, you don't need to define a random variable. So we say that some random variable have some probability distribution, right? Yes, and we talk about random variables all the time. But we can talk about the probability distribution itself because it is a function with some properties, and that's it. So we will talk about the Cdf. We will talk about the density function and so on, and after that we will get back to the random variables. Okay, so these functions, so we are just describing these functions, and this is the Cdf, the cumulative distribution function. And again, by definition, this is just, so f of x is the probability of this set, right? Of this set. So the measure of this set. Okay, good. Now let's think about, so let me write like the meaning of this. Maybe this is not clear. So this is the probability that we get a value less or equal than x, right? It's just like that. This is this function. Now, let's talk about the properties of this Cdf. Yeah. So first of all, if you remember a theorem, we talk about the Doris theorem, right? And in this case, so let me state that again, but using just Cdf and the distribution. So look, if we know that if f1 equals f2, right? So we have two different Cdf, and they are equal. And this Cdf, it's okay, I'm going to explain just the meaning. So we get this Cdf from some P1, from some probability distribution P1. Okay, and we get this f from some P2, right? So from P we get f. So from P1 we get f1, and from P2 we got f2. But if f1 equals f2, then P1 equals P2. Doris. This is not Doris. This is a consequence of the Doris theorem. So this is a consequence of Doris theorem. So it means that for every f, for every function f, there's a unique probability distribution P. For every Cdf, there's a unique probability distribution P. And for every probability distribution P, there's a unique Cdf f. Okay? And this is the same that we have in the Doris theorem. So when we had a semi-ring, so when we have a sigma algebra, and we define some measure of this sigma algebra, then the measure of the sigma algebra and the measure of the semi-ring were exactly the same, unique. So somehow it means this, right? So for every probability distribution, we have a unique Cdf. And what it means is that we can, if, let me write that here, if we want to describe, right, describe with P, right, describe the probabilities for every b from the Borel sigma algebra, right? It's enough. It's enough to define the probabilities for the following set, for b being equal to minus infinite to x. Okay, so if you want to define the probability for each Borel set, you don't need to do it for each Borel set. You can just do it for these sets, and this is enough. So this gives you the whole image that you need. Okay, that is why if you want to describe P, all that you need is F, no more. You don't need to think about P, you only have to think about F, right? Good. And I sent you some video on YouTube about this theorem, kind of the Doris theorem, and he explains really good all of this. So please check that video. Good. Now, let's talk about the properties of the Cdf. But before talking about the properties, let's think about how this function look like. Yes. So if we have, so right now we are talking about the real line. Okay? So next class we will be talking about Rn. So in any dimension. Yeah, of course, because we have random variables, right? But we also have random vectors. So you can have a random vector is just a collection of random variables. And for this, you can describe exactly the same. All you have to do, so if we had here R and the Borel sigma algebra of R, then next class, or maybe in 2 weeks, we will be talking about R, N, and the Borel sigma algebra on Rn. So here we talk about, we will be talking about random variables, and here we will be talking about random vectors. And we will define the Cdf for vectors and the Pdf for vectors and so on. Okay. Yeah, it is. So we have properties. Okay, so look. What is the probability that, so let me remind you, this is the definition, right, of the Cdf. Now, if we have two different values, right, x1 and x2, of course, the probability that a number is less or equal than x2 is bigger or equal than the probability that this number is less or equal than x1, right? This is clear, I think. So, of course, this function is non-decreasing. Non-decreasing, all right? So, the first property is that non-decreasing function. What do I mean? It means that f of x1 is less or equal than f of x2 wherever x1 is less or equal than x2. Okay, so if, I mean, this is, for example, -2 and this is 2. The probability that the number is less or equal than 2 is, of course, at least the probability that is less or equal than -2. That's clear, I think. Okay. So let me prove this. Let's prove it. And to prove it, we only have to do the following. So all we know about the Cdf is the definition. This. So f of x1 is equal to what? The probability or the measure from minus infinity to x1, right? Wait, so, but before that, we have minus infinity to x1, and we know that this set is contained by this set. Right? And by the properties of P, so if we know that A is containing B, then the probability of A is less or equal than the probability of B. Right? So we have this, and then we can see that this is less or equal than the probability. So since this set contains this one, to x2, yes, right? So x2, yeah. And this is by definition, this is just f of x2. That's it. We obtain that f of x1 is less or equal than f of x2. Right? So all that we know is the definition of the CDF. And using the definition, we have to prove the properties. Okay? Good. Well, now let's take a break for a couple of minutes and we'll continue. Okay? Ashish, David. But David is here in Rush. So you should be here. It doesn't count that you are from
Yes, sir. Yes, sir.
Zoom.
So actually, I was tired today because we had PE, and that's why I was too lazy to come. But from next time, I'll come.
Yeah, because it doesn't count. I mean, you are watching
Okay,
the
okay.
lecture and that's okay, but you have to be here.
Okay,
Right?
sir. Okay.
So look, we already proved the first property. Okay? So this was the first property. No. But you said before that it wasn't. You're talking about the PDF. Okay, we will get to that. All right. So this is the first property. All right. Now look, by definition, again, we have that this is the CDF, right? Now, what if x tends to minus infinity? The probability give us equal to 0, right? Because what is the probability that a number is less or equal than minus infinity? 0, right? And what if x tends to infinity? Yes. Because the probability that this number is less or equal than plus infinity is 1, right? So we should get this function should be something like this. Here we have 1, right? And then the first property is this one. Of course, we can see that here we have f of x2, and here we have f of x1. And we can see that f of x2 is greater than f of x1, and they can be equal, right? Now let's look at the second property, and the limit that I'm talking about. So the limit of f of x when x tends to plus infinity is 1, right? You can see that. And also the limit of the CDF when x tends to minus infinity is 0. I'm trying to get not too much. Ah, it works. All right. So let's prove it. So first proof, let's prove which one? Let's prove this one. So let's introduce some sequence, real sequence of, sequence of numbers, which tends to x. No. No, which tends to minus infinity, sorry. So this means that we have a sequence, and this sequence tends to minus infinity, right? I don't know, minus 1, minus 2, minus 3, minus n, okay? And we can do the following. So the probability, okay, let's find, yeah, so we can see that the set minus infinity to x1 is contains minus infinity and x2 and so on, right? Because we have here 0, this tends to minus infinity, so we have here x1, x2, x3, and so on. This tends to minus infinity, okay? So this is true, right? So, and we call this sequence how? A decreasing sequence, right? So we have contain, every time it's smaller, smaller, smaller. So the limit of xn, well, no, sorry, not the limit of xn, but in that case, probability cannot be negative. Therefore, the limit is x times negative zero. Kind of just by knowing basic probability. No, because I mean you just define a function, and you know nothing about this function, you know. So it's obvious that, like I told you before. So what is the probability that this is less or equal than minus infinity? Of course, it's going to be 0. Yeah. But prove it, right? Because we have probability theory, so all of this is mathematics, right? We can apply some real world things, but still this is mathematics. So if everything works, so you can prove it. If you cannot prove it, something is wrong, right? So we have that. Now let's look at the probability. Look, let's look at the probability of the intersection of all this of minus infinite and xn and n from 1 to infinity, right? So we have again a decreasing sequence of sets, and we want to find the probability, and we know a property from the probability that this is equal to the limit of n tending to infinity of the probability of this. So we had here the limit inside, we can take it out, right? And now by definition we know that this thing, this is just f of xn, right? So we already have the limit of so we have this, right? So we can change, so this is just the limit when x tends to minus infinity, so we know that xn tends to minus infinity f of x. And we know that this intersection is empty, right? Because we already said that the limit of a decreasing sequence of sets is empty. And this is obvious, right? So this probability gives us 0. So we obtain that the limit is 0, right? So look, this is not difficult at all, but you need to know how to prove it. You need to know that you just have to use the definition of probability, no more, right? But you need to know that. So we define that, and in the same way, right? In the same way, we can define, we can prove the second part, this one. So how do we prove this one? Again, but this time xn tends to plus infinity, right? So we have that minus infinity x1 is contained and minus infinite x2 and so on. So we have an increasing sequence, right? Then the probability of the union n1 to infinity of minus infinity and xn right? So we take the limit out. So this is the limit when n tends to infinity of the probability of from minus infinity to xn. Wait. So by definition, this is just f of xn, right? And then this gives us the limit when x tends to infinity of f of x. But this is what? So xn tends to infinity. So we obtain what? The union of this minus infinite to plus infinite. So this gives us r, right? The set of all the real numbers. And this is the sample space. So this probability is 1. Yeah. So look, xn tends to plus infinity, right? So this tends to 1, right? That's it. Good. So we have, this is the second property. The second property of the CDF. Now, the third property is the following. This function is continuous from the right. Right? So it means that, what does it mean that it's continuous from the right? So we know that a function can be continuous from the right or from the left, and a limit exists if and only if both limits, so the limit from the right and from the left and from the left is the same. In that case, the limit exists, right? From calculus, you know that. So look, we have again this function. So this function is not continuous in general, right? So we can have this. This is 1. maybe there's some point, call it A, in which this function, the Cdf, is not continuous. F of x, right? Then in this point, this function has to be continuous from the right. Means that here is f of a, and here we have this, right? So the limit from the right is just, well, it's defined, right? So it's continuous from the right. You know this. So we have to prove this also. Let's prove it. But now in this case, look, here we have that xn tends to minus infinity, xn tends to plus infinity. So now let's take, instead of a, let's take x sub 0, right? So xn tends from the right to x0, right? So we have a sequence of numbers, and this sequence tends to x sub 0, all right? Then what? How to? So we need to show the following. We need to show that the limit when x tends to x sub 0 from the right of f of x is equal to f of x sub 0. This is what we need to prove. This is the definition of a function being continuous from the right. Now, how do we do that? So let's look at this. So f of x sub 0. So we know that by definition, this is what? This is just the probability of the number, right, of being between minus infinity and x sub 0, right? Just by definition. And now we know that, how can we change that here? We know that xn tends to x0. Yeah, we can change this. So the probability of the limit and n tends to infinity of minus infinity. Here we have xn. No, not this way. Just on the right. Then we need the intersection of all of this. Yes. Again, please. What is equal to? No, look. So look, we have, for example, here, so we have this sequence, x1, x2, x3, and so on. This sequence tends to x sub 0, right? So it means that we have this set. So we have minus infinity x1, right? Then this set contains the set of minus infinity x2, and so on, right? So we have a decreasing sequence of sets, right? And we can see that this is equal to this one. So if we get all of this, like this, like this, like this, all of them, the intersection of all of this is going to give us from minus infinity to x0, the intersection, right? The countable intersection. And now we can use the property, continuity property, over here, and this is the limit when n tends to infinity of the probability of minus infinity to xn right? And this is what? This is just f of xn. And we know that xn tends to x0. So this is again the limit, and n tends to infinity of f of xn. And this limit is just f of, no, wait, this, like that. And that's it, right? Because x of n tends, so we can change this like this is equal to this. So xn, when n tends to infinity, tends to x sub 0 from the right. So this is the same of the limit when x tends to x0 from the right, f of x. And we got the answer. So we proved that this thing from here, right? That's not a very good idea to do that. Is equal to this. So this function is continuous from the right. So this is the third property that we need to prove. We needed to prove. Sorry. Because here we have, so what is the limit of xn when n tends to infinity? This is x0 from the right. Plus 0 means from the right. Yes, plus 0 means from the right. So this is tends to x0 from the right. And if it tends from the left, then it's minus 0. Yeah. So that's it. We proved the things that we needed, right? This is something. Yeah. Good. Now, we've defined a function, a Cdf, and for this function we have three properties. Now we can state the following. So this is a lemma. So any function f for which properties 1, 2, 3 are whole, if how to write it is a Cdf of some probability distribution. So what do? We already know some functions, and we know, yeah, this is a Cdf, right? But now we can do actually the following. You can take absolutely any function such that property 1, property 2, and property 3 are true, right? And this function is a Cdf. Okay, so it's not only that a Cdf has these properties, but it's also that for any function which these properties is a Cdf. All right. So everything that we need to define a CDF is defining a function such that these properties are true, right? Yeah. So look, when we define the Bernoulli distribution, the Poisson distribution, and so on, right? So we can think about why are these, are these the only distributions we know? How many distributions are there? Well, there are infinite numbers, because how many functions do we know that we can create these functions such that these properties are true? There are, I don't know how many. Yes, so they are important because the experiments that that they describe are very popular, or very, I don't know, in thermodynamics, for example, you have the Bernoulli distribution, the binomial distribution in thermodynamics and statistics, physics, and statistical physics, a lot, right? And so on. So that's why, but any function which these properties is a CDF of some probability distribution. And that's huge, right? This is difficult to prove, so of course we are not going to do it, but don't forget about that. Now, right, so we already know everything about the CDF. Now we can describe the CDF of some distributions that we know, right? So let's talk about the distributions that we already know. So probability distributions. So as we know, so there are three different kinds of probability distribution. The first one, discrete. The second one is continuous, absolutely continuous. And the third one is singular. So there are three different kinds of distributions: discrete, absolutely continuous, and singular. We're not going to talk about the singular distribution, but all I can tell you, and actually I already said something about that, is that the Cantor's set, right? The Cantor set, which is a set of numbers from 0 to 1. So there's a set of numbers from 0 to 1 that we call the Cantor set, and this Cantor set is very important because this is an uncountable set which have measure 0, right? So this set is uncountable and it has measure 0. And from this set we can create a function which looks like this. And it's called the Cantor's function, or in English they call it the evil, how to say it? The evil stairway, or something like that. Yeah, evil something, or the devil's some, I don't remember. Why? Because this function defined on the Cantor set is a singular distribution. It's the example of a singular distribution. Why? Because the probability here is 0. Why is evil? Because we are talking about a set with infinite number of elements, which is equivalent to the set of the real numbers. So this set has as many numbers as all the real numbers. Yes, exactly. But the measure of this set is 0. You can see it. So look, we have the set of real numbers. Well, actually like this, right? The measure of this set is infinite, right? The measure of from 0 to 1 we define it, for example, if we are talking about the Lebesgue measure, we are talking about the Lebesgue, is 1, right? So, but the Cantor set is a set with the same number of elements in here, but the measure is 0. Well, that is why this is called an evil something, because it's weird, right? The evil or the devil stairway or something like that. All right, so it's very cool, but this is something from logic, from mathematical logic. We're not going to talk about this. Just this is very cool, so I wanted to give this introduction, right? So we have this singular that we're not going to talk about, and we have then the discrete that you already know very good, and the absolutely continuous. Now let's talk about the discrete distribution, right? So in the discrete distribution we have a set X, right? So discrete. Again, we have not talked about random variables. All right, we are talking about just the function, discrete distribution. So we have some set X of the real numbers. And what do we know about this set? This is finite or countable. This is all that we know about this set, right? So, for example, the set of the natural numbers from 0 to infinity, or just 1 and 2, or just 1, right? So any discrete, let's call it like that, discrete set. And we know that the measure of X is 1. So if we put all together, then the measure, the probability is 1. And yeah, pretty much that's it. And how do we define? So how do we describe the any discrete distribution? So again, we have Cdf, right? Right. But we didn't talk about the Cdf previous semester, right? We talk about something else. What is the name of this function? No, we haven't talked about the PDF. Huh? The probability mass function. Yes. So the probability mass function. Probability mass function. PMF. So CDF, PMF, right? So in English it's like, in Russian it's not defined like that, but yeah, just distribution and function of this of distribution, what we call a CDF. All right. No, of course not. They are different. They're different. Why? Because look, we have a discrete. Again, we have this discrete probability distribution, right? We need to describe it somehow. We say, okay, let's use the CDF, right? We can use the CDF, but to use the CDF here is silly because you can use something even better. You can use the PMF, the probability mass function, right? So the probability of any X, so this P, we call this, this can be called discrete density, right? So either discrete density or probability mass function. In English, in the English world, they call it probability mass function, all right? So the probability mass function of any X, where X is just an element of capital X, is just the measure of this set, right? So we take the element X, and we can define the probability of this element. So this P is probability. It is the probability measure, right? Probability distribution of this. And we call this the probability mass function. And this is all that we need to describe everything, right? But of course, we can define this the CDF. And if we talk about, for example, the Bernoulli, okay, so let's So let's talk about first the Bernoulli distribution with parameter p. In this case, x is what? So we only can have 2, 0, and 1, right? We know that we get 0 with probability 1 minus p and 1 with probability p. P is some fixed number from 0 to 1. Now, how does the Cdf look like? We have here 0, we have here 1, this is x, this is f of x. Let's try to draw this function. So we know that somehow this function should be like this, right? So non-decreasing, the limit when it tends to minus infinity is 0, the limit when it tends to plus infinity is 1, and it's continuous from the right. So these three properties, right? So there are two key points here, 0 and 1. What is the probability? So take any x here, x 0, less than 0. What is the probability that of this set? Right, because this is we're talking about Bernoulli. So what is the probability that we get minus 5? 0, right? So the probability that we get any number less than or equal than 0, wait, less than 0 is 0. Wait. So any number here, the probability that we get a number less than this x 0 is 0, right? Now, what is the probability? And now we reach this point, x1. What is the probability that we get a number less or equal than 1 over 2? No. Look, what is the probability that we get a number less or equal than 1 over 2? What options do we have? We only have two options, 0 and 1. Which number is less than 1 over 2? 0. Yes. So for every number less than 1, it means the probability that we get 0. So 1 minus p. Here we have 1 minus p. And for all these numbers, the function is like this. Right? Don't forget about the definition of the Cdf. It's the probability that we get a number less or equal than this one. Right? So the probability that we get a number less than 0.9 is equal to the probability that we get 0. So 1 minus p, right? Now, what is the probability that we get a number less than 2? Yes. So we have two options. It can be both 1 and 0. So the probability is 1, right? So it's 1 here. For all the values here, this is 1. And what do we know about this function? This function is continuous from the right. So it means that here we have like this, and here this point. Here we have like this. Here we have a point. No. Yeah, because we haven't talked about the CDF. That's for sure. So that's it. This is the CDF for the Bernoulli distribution. Now, Yeah, what's going to be the difference? Yeah, so we have a lot of steps, right? Now, look, in every point, so we only have two options, 0 and 1. 0 and 1. Look, this distance from here, and this is something we're going to prove, but right now I can tell you, this distance gives you the probability that you get 0. So this is the probability that you get 0. And this distance is the probability that you get 1. Right? So here we have 1 minus p. So look, 1 minus p, and here this is p. So this distance is p. And of course, p plus 1 minus p gives you 1. Right? So if you have some CDF like this, and there's some point A, then, and the question is, right, this is maybe some question for the exam. What is the probability that the random variable, right, is equal to A? All you have to tell me that is this distance from here. This distance gives you the probability that of this point A, okay? So let's say the random variable gives you A, right? And this is actually something that we have to prove, okay? So that's it. We talk about the Bernoulli distribution. We will talk about the binomial distribution, the Poisson distribution, and next class we will be talking about the exponential distribution, the normal distribution, the gamma distribution, and what else do we have? And yeah, and that's it, right, for the distribution. So that's it for today. I mean, for the lecture, right? We still have seminar. All right, guys. So um, so do you have any questions about the theory? No questions? All right. Cool. So we had homework, right? The first exercise, which one was that? Let me see, I don't remember. Okay, I see. Who did the first one? The first exercise. The first. You did the last one. Yeah, that's the difficult one. Cool. Okay, so first of all, by the way, yeah, I need to check attendance. Wait a second. So who is here? Who's not here? So Coffee is not here, right? I mean, is he coming back? Do you know? Or what? Let me find you. I don't attendance. Here. Okay, so Krutika is here. Well, it's over there. Then we have Gomez Santiago is here. David. Okay, let's say that you are here, David. David, not but Ashish, right? Ashish is your name. But this is the last time, right?
Yeah, last time. We have no PE now, so that's why.
Yeah, I can see that, but I was in class as well, so you are not my first class today.
Okay, thank you.
Rohan, that's you, right? Daniel is you. Monica, I think, yeah, she's here. Can you hear me, Monica?
Yes, sir.
Great. David, that's you? No, wait. Yes. Sorry. Coffee is not here. Mijael is not here. And Jimenez, Gabriel Antonio, not here. So you remember how, so if you miss more than 2 or 3 classes, you don't get a point or something like that. I don't remember. So don't forget that. Yeah, if you come to all the classes, of course, you get 1. If you miss at most 2 classes, then you get 0.5. And if you miss more than 3, then you don't get anything, I think. But it's 1 point from 10, so. And is that an extra point, I think, no? Extra point, no? Yeah, I don't remember. So there are different courses, there are different graces. Then it's not extra, yes. Okay. All right, so the first exercise, look, we have, so I have to solve it, right? I see that. Maybe, well, Krutika was here, but she left. Yeah. Maybe Monica knows. Monica, do you have a
I didn't do that one, sir.
All right. Okay, let me do that myself. So look, we have, so this is the first exercise. What do we have? We have a set of n numbers. Yeah, let's say numbers of n elements. Okay, so 1, 2, n. You can call it S, right? So this is a set of n elements. And from here, we can randomly, we can take subsets, right? So we can take subset AI. So what do? We look at the, for example, it's like having a box here, and we have the balls, n balls, right? And we look at each ball, and with probability p, we take this ball, and with probability 1 minus p, we don't take it, just like that. And we do that for each ball, and at the end, we get some set, AI, right? So this is some subset of S, okay? And I think with n elements, no, just like that, right? And we have so I goes from 1 to m. So we have m subsets of S, right? The number of elements in each AI we don't know. Maybe it's empty, maybe it's n, maybe we took all the balls this time, maybe we didn't, right? We don't know. So we have here A1, we have A2, we have A, that's m, right? And here we have some balls, and here we have another balls, and here we have some. Maybe it's empty, maybe it's full of n balls, and so on, right? That's it. Now, the question here is, what is the probability that the number of total balls is k? Wait, no, actually, wait. Yeah, in that case, no, yeah, that the union, so that the number of balls, so maybe we have one in, maybe we have 1 and 1 here, so we don't count these 2 times, right? So what is the probability that we took out k balls after taking out all the balls, I mean m time, right? That m k balls out of here. So in other words, what's the probability that the union, and that not like this, but that the union of A1, A2, AM equals K, right? This is the same. Yeah, so you see how, who is Serafima Sherbina? Is this some new student or no? All right, first time I see. Okay, so how do we find this? Well, somehow we need the Bernoulli distribution, yeah, because this is actually these subsets are called random Bernoulli subsets or something like that, random binomial subsets. Okay, but look at this in the following way. Here, 1, 2, 3, 4, n. Okay, this is then each of the elements from S, right? Now, here we'll have A1, A2, AM. Yes, exactly. So look, if the ball number 1 is in this box, then we write 1. And if it's not, then we write 0. So we get here 1, 0, 0, 1, no, 1. Yes. Almost, yes. So we need two things. We need that in k positions, right? So yes, wait. So look, for example, this is k. So in k positions, we need at least once we have 1. Yeah, in every column we have at least once we have 1. Maybe 2 times, maybe 3 times, and so on, but at least 1, right? And the other has to be empty. So here, in every column, we need at least, so 1, at least 1. Yeah, yes. So look, and here we have only zeros. Zeros, right? So here we have n minus k, right? For example, we have here 1, 1, 0, 0, 1, 0. Or maybe we have 0, 0, 0, 0, 0, and 1, right? And all of this has to be 0. In that case, this is true, right? So how do we define this probability? So this is equal to the probability that we have at least, that we have 1, at least 1. This is what? Yeah, well, tell me. That's all. So first of all, the success is P. It's going to be Bernoulli distribution of P, comma, M, because there's M cases. That's going to be the Bernoulli distribution. Look at the word at least. It's 100%. No, look, you need at least, so 1 need to be here at least once. So maybe 1, maybe 1 time, maybe 2 times, and so on, right? So let's look at the probability that we don't have any 1. and then the probability is going to be 1 minus this, right? So 1 minus the probability that we don't have any 1. So that's 1 minus p. How many times? M, right? Because this is m times here, right? And how many times do we need this? To the k, right? So k times we need this. And now we need that all the others are zeros. M minus k, right? And what else do we need to add here? No, so look, we fixed here the position of the k elements, but we can change that, right? So maybe the k elements are this, maybe the k elements are from here, maybe from here, well, I mean from here. So how many options do we have to choose these k elements? So we have to choose k elements from n. So n choose k, right? That's the answer. Right? Yeah. Okay, now let's do something else. Let's say that we don't have m subsets, but we have only 3. A1. Okay. So is that clear for everyone? Yes? Clear? Okay. So we have only A1, A2, and A3. And we want to find the probability that A1 is a subset of A2 union A3. The same logic, right? So look, we have 1, 2, 3, and we have A1, A2, and A3. Now let's look at the following. We have to look at all the possible options that we have. And we need to look at the options that we need, right? So what options can we have? How many options can we have here? So we have, for each of them we have 2, right? So 2 times what? So look, maybe we have the following: 0, 0, and 0, right? Maybe we have 0, 0, and 1. What else? So 0, maybe we have 0, 1, and 0. We have 1. I mean, we don't need this here, right? Just 0, 0, right? 1, 1, and 0, 0, 1, and 1, 1, 0, and 1, and 1, 1, and 1. 1, 2, 3, 4, 5, 6, 7, 8. These are all the possible options, right? These are all the possible cases every time. And this is for a fixed position, right? For any fixed position, we can have one of these options. Is it clear why? What happened here, for example? Take the ball number 1. Let me do it in a different color. In this case, in the first case, we don't have this ball not here, and not here. Right? In this case, we don't have this ball here, here, but we have it in this box. So how many options do we have? We have eight options, right? How many of these options are good for us? Actually, let's do it this way, like okay, let's say. So which of these options, it's better if we write 1 here, 2 here, and 3 here. Just better because we did that way. Okay. So A3 is a subset of A1 union A2. So it is good for us. Yes, it's good. This is bad for us. It's fine. So this is fine and fine, right? No, no, wait. No, this is fine, right? Because we have 1 here, 1, 0. Here. Right? So only one case is not good for us. This case. So what do we need? So we need 1 minus the probability that, so the probability that this is true is equal to 1 minus the probability that we get 0, 0, 1. Probability of this 1 over 1 over 1 over 2. Yeah, wait, not that way, but we have to talk about P and 1 minus P, right? Success and failure. This is not classical. This is Bernoulli, right? Bernoulli binomial, right? So the probability that we get 0, 0, 1 is what? Is P squared times 1 minus P. Sorry, the other way. 1 minus P squared P. Yeah. No, this is just look. You need 1 success, 2 failures, right? So 1 success and 2 failures. That's it. All right. So let me check if I'm wrong. Well, this how many times? Yeah. So this wait, this is not all, right? So this is the probability that it's okay, right? And one minus this is the probability that for this specific ball, this is true. But we have n of them, so this is all to everything to the n. Yeah, so for each ball, for each element, we have this. So for all the elements, we need n times. Okay. I think that's the case. Let me check. I just want to be sure that I'm telling you the truth. Is that somewhere here? Wait, where is that? Mm-hmm. Okay, so this is P1. Yeah, it looks okay. Mm-hmm. Yeah, that's the correct answer. Okay, good. Now next, who wanted to do the second one? Okay. Okay, let's start with the second one.
I'm not sure if I have the right answer, but I will try.
Well, let's try it.
So, this question is
No, wait, just do you have any question about all of this? Maybe you have any question there on Zoom? No? Everything clear? All right.
so, if I remember correctly, so we have 4 cubes.
Mm-hmm.
I'm just, so there are 4 cubes. Only 3 of them, half of the faces are painted white, and on the 4th cube, only 1 out of 6 is white.
Yeah.
The randomly chosen cube is rolled 7 times. Find the probability that the 4th cube was chosen if on 7 tosses the white face falls out exactly 1.
Mm-hmm. But by the way, sorry, do you remember that this exercise and this exercise were on your test?
Yeah, something very similar to that. I had a few.
So this was on your test, and the next exercise also.
Yeah, that's why that's why I had this idea. I had titled understanding, but
yeah. So we already did all of this actually.
yes, sir.
Mm-hmm.
But for this one, it's conditional probability. So the conditional probability of the probability of course, us getting the 4th cube if we get the white side on the 7th row, something like that. Or
no, if we got the white side exactly once.
Exactly one. Out of 7 rows, getting exactly
yes.
So going forward with the definition of conditional probability, we can get the following consequences. It's C4 intersection white 1 after 7 rows over white 1 probability. So we get something like this.
Mm-hmm.
For the definition. But here, so I had a bit of a mistake when I first solved it, but then I see my problem. I'm still my mistake. So this one is kind of difficult. So what I did, I thought to myself, how can I simplify it? Well, this is kind of difficult to work with, and I wanted to change this, and I wanted to make it a bit different. So what I thought of multiplying it by probability of D4 over getting cube 4 and probability of cube 4. In retrospect, this is equals to 1, so it's going to work out fairly well. And the reason I did that is so that we can have something of the following conditions: the probability of cube 4 falling out in intersection with the white 1 falling out on the 7th row over the probability of, I'm going to get cube 4 here, multiplied by probability of C4 over probability of W1. So this is allowed.
Yeah.
The reason that I wanted to do this step is because we're going to get a conditional probability of actually probability that we're going to get a white 1 when on the 7th row if we get the 4th cube.
Mm-hmm.
So this is fairly simple. So before we calculate this, we can calculate this. The probability of us getting the 4th cube is 1 over 4.
Mm-hmm.
The probability of getting a white 1, of course, it's going to be binomial distribution of, if I'm not mistaken, it's going to be 1 over 6.
Wait. So this is the probability that you get at exactly one with a white side, right?
Mm-hmm.
Yes. But you have two options.
Yes, sir. So the first option is 1 over 6 with, so 7 times. So 1 over 7. Sorry. It's going to be binomial distribution of 1 over 6, comma 7, plus binomial distribution of 3 over 6, comma 7.
Well, the other way, by the way. So 7, 1. So this is NP, right?
Oh, no, I was right, PN. That's my, mine is, I don't know if it's right, but I like to do this.
PN? It's MP, but, or PN? It doesn't matter, but just, I mean, if you do this, then write like P to be clear, because I think that they are different. Yeah.
Now, the interesting part is of getting this. So
yeah, but what is the meaning of this?
Not a problem. So it's gonna be n choose k. So since k here, if we could get 1, so n k equals to 1.
Yes, that's correct, but there's something missing. So what is this? This is the probability that you get exactly once this white thing if you choose the fourth die, right?
Yes, sir.
But you still have to multiply by the probability of choosing the fourth die,
Ah, yes, sir.
right? Because this is total probability formula.
So this is of course 1 over 4, and here is multiplied by 3 over 4.
Yes.
Yeah, sorry for that, sir. My bad. And now for this one, well, this one is basic. I can create decision tree. That's what I did. So yeah, and also this one is doing decision tree, but we can create here and here. So here we choose the fourth cube, and here we choose 1 to the third cube. And here is going to be 3/4, and here is going to be 1/4. Now from here, all of this is going to be basically a binomial distribution. And binomial distribution of 1 over 6, and 7. Then to get,
Wait, what are you doing? You are finding this?
yes, sir.
Oh.
Yeah, because in the end we managed to do it. And this one is going to be equal to 1 over 4 multiplied by binomial distribution of 1/6 on 7 tries. So now, since we could like substitute every one, we could find the answer here. I just didn't find the answer because
So this is correct. This one is good. And this is 4 is 1 4. You have 4 options for yeah.
simple.
That's it. So let me just this is correct. Okay. Let me just explain you a bit different. Look. You can just come here, and you can get the Bayes formula, right? So this is Bayes formula. I mean, this is exactly the same, right? But so this is what? This given C4 times what? C4, right? Yeah. Yes. Yeah. And this is the probability that we get the white side exactly once. So we can divide this into two possible situations. That we get a die. That we get yes, a die. So we have 1, 2, 3. So we have 3 dice, right? Such that half of the side is white, and this is only one side is white, right? So we can say that if we choose one of these dice, then we let's say that this is the event H1, choosing one of these, right? And choosing the fourth one is H2, say, right? So it means that if we want to get this, we can use, this is exactly this, right? But just writing using the Bayes formula like right away. So this is the probability of omega 1 given H1 times the probability of H1 plus the probability of omega 1 given H2 times the probability of H2. Right? So this is exactly this. Right? And that's it. So you can compute this and you get your answer. So this is, don't forget Bayes formula. Okay, good. Yeah, that's like that. The answer is going to be 0.7 or something. Yeah, we don't need to answer. So I mean, that's useful, of course, but that's not the main goal. Yeah. So This was the second one, right? Now let's continue with the third one. Which one is the third? I think that the third one is the one that I don't remember how to solve. Let me just see. Yeah, this one I'm not sure. So let's just skip it. So let's do it next class. All right? Because I don't want to improvise here. I don't remember exactly. And the last question, yeah. So somebody here wants to solve it. But before that, how do you want to solve it? Hmm? Who wants to solve it? You? Whoever wants to solve it, please. Yeah, you? No? Okay, what do we need to prove? So we have that. So this is the fourth one. Again, the number 3 next seminar. Okay, just not sure. So we have these events, and we know that they are independent, right? And if I say that they are independent, it means that they are mutually independent. Okay. Now I need to prove that the probability of the union of these sets is just 1 minus the product 1 to n of the probability of the complement. Okay. Look, the first thing you have to look at here is this. You have 1. We're talking about probabilities, and you have 1, right? So what the probability of what give us 1? Right? The probability of omega. So for example, if we have omega here, the probability of omega give us 1, right? And we have this A1, A2, I don't know, and A3 and so on, right? And we want to know the probability of the union of all of this, right? It means that somehow we need to get the probability of omega. So we can express it like this. The union of from 1 to n of AI is equal to omega minus the complement minus the union of 1 to n of the complement of I. Right? So let's wait. The intersection. Okay, look, we have omega. Now we look at the complement of A1 going to be this. Right? Now we look at the complement of A2, and it's going to be this. And yeah, and we look at the intersection, and at the end, the intersection is going to give us this. Everything but the union, right? So take omega without this, and of course you get the union of all these sets. So this is this. So this is true, right? Good. Now, we know that the probability of A minus B, if A is contains B, is just the probability of A minus the probability of B. We can show that easily. And then we get that the probability of the union of all of this is the probability of omega minus the probability of the intersection from 1 to n of AI complement. Yes. So the elements in A, but not in B. Okay. So good. Look, we have this is 1. And what is this? Yeah, so what do we know about, well, the probability of A intersection B is equal to the, so we need the product, right? The product. So we know that this is probability of A times the probability of B if and only if A and B are independent. Are these events independent? We don't know. We know that A1, A2, and so on are independent. But here we are not talking about A1 and A2, we are talking about the complements. So we need to prove that these events are independent also. So they have to be independent if this is true. How do we do that? This is the key question here, right? By induction, all right? So let's do the following. Say we have A1 and A2. Let's assume that they are independent. Prove that A1 and the complement of A2 and also A1 complement with the complement of A2 are independent. So we know this, we need to get this and this. So we prove it for 2 sets, only 2 events. And then using induction, we can get that if we have n events, then the complement of each of them are also independent events, right? Now, how do we prove that? So, look, we have A1 and we have A2. We know that the probability of A1, A2, so the intersection, if we have the intersection, we don't write intersection just like that, is probability of A1 times the probability of A2. And we want this, right? So we want to write here complement the complement. So let's do the following. So let's find the probability of A1 intersection with complement of A2. Right? This is what we need. So what is that? A1 intersection with the complement of A2. There's this. Right? But we can also write this. So the complement of A2, so we can change that, write it in this color. So it's going to be the probability of A1, the intersection with A1 intersection the complement of A2. It's the same, right? So this. So we are taking A1 and we take out A2. but we are taking out only this part of A2. So we are taking out the part of A2 which is in A1. So this here, we can change it by this, right? Because we are taking out only this part. So we have right. And then what? A1 intersection this. So this is like taking, this is equal to the probability of A1 minus this. A1 intersection the complement of A2. Right? So we have this, we are taking out this. This is the same, right? So look, here we were doing what? Take A1 and wait, no, this the complement. Oh, wait, no. The complement of A2, that's that. We look at the intersection. The intersection was this. So this, let me write that. So this is A1 intersection complement of A2. Then we can change this A2 with no, wait. The following way, sorry. So probability of A1 intersection A2 complement is the same that the probability of A1 minus A2. Yeah. So this is what we need, right? This is the same than this. So the intersection of A1 with the complement of A2 is this. We don't have back here. Right, is this. This is this. This is the same that A1 minus A2, right? But this is the same to probability of A1 minus A1 intersection A2, right? And this is the same that we did before. So we have, of course, that this is equal to probability of the probability of A1 minus the probability of A1 intersection A2, right? And what do we know? We know that since A1 and A2 are independent, then this is the probability of A1 times the probability of A2, right? And then we obtain that this is the probability of A1 times, and here we have 1 minus probability of A2. No, look, we take out A1. So this is the probability of A1 minus the probability of A1 times probability of A2. Yes? We have a common element, A1. We take out this element. We take the probability of A1 times 1 minus the probability of A2. And 1 minus the probability of A2 is the probability of the complement of A2, right? So this is probability of A1 times the probability of the complement of A2. So we got that the intersection, so the probability of A1 complement A2 is equal to the product, right? So we already got this one. Now, how do we get this one? How do we get this one? Who can tell me? So do we need to do something else? Or can we say this follows already? We can say that this follows, right? Because we have the following. If we have two events which are independent, it means that this event with the complement of this one are independent. Now take this one and this one. And we can say that this event with the complement of this one are also independent. So we got this automatically, right? We don't need to do this again. We just applied everything that we know. So we obtain that if two events are independent, then their complements are also independent for two events. And how does it follow, right? How does it follow? How do we apply induction here? We need to apply induction. So how do we apply induction? The big question, right? So look, we already know that for two events this is true, okay. Now we need to show the following. We know that we have A1, A2, and AN. We know that they are independent. We know that the probability of their intersection is just the product of the probabilities. We know this. This is given, right? We assume that this is true for n. Wait. Assume that we already proved this for n. So that A1, if A1 and AN are independent, then A1 complement AN are also independent. Let's assume this. This is the step of induction, right? And now we have to prove that then A1, AN plus 1 are also independent, right? We prove it for 2. Now we get for any n. So the probability of A1 intersection A2 intersection AN plus 1 this is what? This is probability of all of this is the probability of omega minus the union. No, wait, the union of all of that. All right. Yeah. So we know that they are independent. This is given, right? Okay. Don't get confused, please. We know that they are independent. We need to prove that A1 complement AN plus 1 complement are independent also. By now we know that this is true for n. Now we have to prove that this is true for n plus 1, right? We can do the following. This is equal to the probability of the intersection from 1 to n of AI times the probability of A n plus 1. This is true because they are independent, right? Good. Now, so it means that this event, let's call this event A, X, and this event Y. So we have two events. These two events are independent. It means that their complement, so that this with the complement of this are independent as well, right? So it means that the probability of so follows. So it follows that A1, AN, AN plus 1 complement are independent. And then we can apply this once again until we get, then in the next step, we get that this and this, n-1 and a1, that they are independent, until we get that all of the complements are independent. And that's what we needed here. We proved that all of them are independent. So it means that this is equal to the product. So this is 1 minus the product from 1 to n of p complement of ai. Right? You can see it. Yeah? Yeah, from now on, we don't have many like combinatorics or something. We have only calculus, actually, right? Yeah, so we finished with this one. Good. Now let's solve some examples related to CDF and PDF. Well, CDF, we don't know anything about PDF right now. Let me just check which one. So, do you have any questions by now? Okay, I hope you don't. Or I hope you do have questions. Let's see. Just a sec. I need to check something. Hmm? Yeah, sure. I mean, no, now, of course, now. We still have 30 minutes.
So should they, will that work until the end of the class? Because we'll have one.
Okay, let me see. Okay, look, first of all, so let's do the following. So this is the first exercise related to the CDF and so on. Let's prove that the probability of like this. No. So let's prove that the probability of getting this half closed interval is f of b minus f of a. So what do we have here? So this is the first exercise related to CDF and so on. So we already finished with combinatorics, with basic probability. We finally start with contemporary probability theory. All right. Now we have to prove this. This is actually kind of obvious, but let's. So do you see it? Do you see this? Do you see that this is obvious? Yeah. Okay. Still, let's prove it. So this is the probability. So this is the probability of what? By definition, this is what? Please tell me. Hmm? So what is F? Yeah, but we are with. Oh, sorry. What is this? So look, we are taking the probability. So this is A, this is B. Here we have close, and here we have close, right? So yeah, minus infinity to A, and here we have from minus infinity to B, close. So we need to take this minus this, right? And this gives us the open interval, the open, so here A, right? A and B close, right? We take this minus this. We are taking out A because this is closed. Here, then we get open here, right? So that's it. So this is this minus this, just like that, by definition, right? Good. Now, we don't know what a density is. Okay. So let's prove what is the probability. So this is the second one. What's the probability that we get the closed interval A and B? We need to prove that this is equal to FB minus F A minus. So this A minus means that this is the function from the left, right? Wait. Just a sec. How do I have it? Yeah, so x tends from the left. Yes, of course. So look, again, what are we looking at here? We have here A and we have here B. We want to look at the probability that we have the closed interval A and B. Then we need this, all of this, minus what? Open here, right? Yeah, look, we need A to be here. Then if we take out the close, then we don't get the answer, right? So we need open. So we need the following. We need this set minus infinity to B minus minus infinity to the A, to the open set, to the open interval A, right? This is what we need, right? So let's do that. So look, this is by definition, this is just the probability of from minus infinity to B. Good. Minus A from the left. So there's something from the left, but not equal to A. What do I mean? Let me just draw this. Maybe like this. This is f of B, and this is f A minus, and this is f A plus, right? So then this is the point A. So from the left, right? And plus means from the right. Okay? Now, this, so what do we need to do here? We need some sequence xn tending to a from the left. For example, a minus 1 over n. Wait, a minus 1 over n. Yeah. So what is the limit when n tends to infinity of this function? Yeah. A, right? Because this tends to 0, right? And this is tending from which side? From the left. Because we have what? We have 1. So this is 1, 1 over 2, 1 over 3. And we are taking out this. So look, we have here a. This is a minus 1. This is here a minus 1 over 2. A minus.
So envision on this graph,
Mhm.
this is going to be the coordinate is here on the left. But why is this not the way? Not the upper one.
Because look, we need the probability that this is between this and this, right? So it's going to be this distance from P. So this is the probability. Okay. Now we have this. So this tends to A from the left. Okay. Now we can do the following. Oh, sorry, not like too much. Yeah, we can do the following. All right. Okay. Take the look. This we need this set. We need this set. Somehow we need to express this set because we need minus this set. So this is equal to the following. This is the union from n1 to infinity of minus infinity and a minus 1 over n. Do you see this? Right? So, right? So every time we are closer and closer to a, we need to the union of all of this, right? So we find that the probability of this union so we have a sequence, and this sequence is increasing, right? It gets bigger and bigger and bigger, right? So this is the first one, second one, third one, bigger and bigger and bigger, right? So by the property of the continuity, I don't care. You got it. This is the limit when n tends to infinity of the probability of minus x and y minus 1 over n. So we can, the limit that we have here, we can put it out. It's out over here. The limit is out. And we just rewrite this. And we can change this because it's going to be better. So this is just xn, right? So this is the xn that we defined at the beginning, right? So we can write that this is equal. So this is the limit when n tends to infinity, or plus infinity, right? Of the probability of minus infinity xm. And this is, by definition, this thing is the CDF, f in the point xn. So this is the limit when n tends to infinity of f xn, and we know that xn tends to a from the left. So this is f of a minus. So the limit of this function when the limit of this function tending to a from the left. So we can see that f of a minus is equal to the probability, and this is this thing from here. This is what, how I say here, minus infinity to a. So we got that finally the probability of AB close is the probability from minus infinity to B, right? Minus the probability, and here we need minus infinity to A. But this, as we proved here, this is equal to f a minus, so to the CDF of A from the left, and this is equal to f of B. So this is f of B minus f of A minus. That's it, we prove it, right? So this is what. Yeah, sure. So, as you can see, probability as we started previous semester is finished. So we are not going to talk about combinatorics and something like that anymore. We're going to talk about calculus. We're going to talk about functions. We're going to talk about the conditions that a function needs to be the inverse of the function exists. We need a function to be continuous. We need a function to have the derivative in some point. So this is calculus already. So probability theory is calculus actually. All right. Yeah. So that's it. Thank you very much. See you next class.